Okay, so let us start with the first lecture of this part of the theory that is about basic image processing tools for cryo-electron microscopy. So in this lecture we will see very basic operations that we can perform on an image. So we will first define what an image is, and then we will see how they are encoded, and then what is the concept of sampling, and then basic operations, and one of the most important operations is the Fourier transform. So an image is a variation of some physical variable over a space. So for instance, here the physical variable is color. So we have an analog image in the real world. For every possible position, you have a different color. But that is the real world. In the computer, you cannot store absolutely all positions, but you have to discretize the space. So that is why you have a regular grid here. But also you have to discretize the colors, and the discretization of the space gives you a grid whose distance is, or this operation is called sampling, while the discretization of the colors is called quantization. Okay, so let's start with the second part, the part of the colors. So how do you encode an image? So let's say that you have a color image like this one, and we all know that colors can be composed as the addition of some primary colors, and in particular red, green, and blue. So let's say that we want to express a red pixel. So what we would do is to put a high value in the red channel and then 0, 0 in the green and blue channels. The highest value that you can have with 8 bits, highest positive value is 255. So we would put 255 in red and then 0, 0 in green and blue. And we would do the same if we want to express a blue pixel. So you would put blue to 255 and the other two channels to 0. Then let's say that you want to express a green pixel, but it is not the greenest that you can ever have. So you put a value that goes from 0 to 255. So let's say just in the middle, 128. And then it is green, but it is not the brightest green that you can have. And if you combine colors in different channels, then what you have is a combination of those two colors. So for instance, if you combine red and green at the same intensity, then what you have is a yellow. And if you put both to the maximum intensity, then you have the maximum yellow you can have in the computer. It turns out that gray images, if you put the same value in the three channels, so you put 255, 255, 255, what you get is white. If you put 0, 0, 0, what you get is black. And if you put the same value in the three channels, somewhere between 0 and 255, what you have is a gray that goes from black to white. And so for instance, if you want to express this image, so and we are making here zoom, what you need to store is only the number that you have to repeat in the three channels. So here we have the collection of numbers for this particular part of the image, and we see that darker regions of the eye here, they correspond to smaller values in this gray intensity values. And the images that we collect in cryo-EM, they are gray images, and so we only need to keep, for every pixel, we only need to keep a number. This number may be normalized, so it doesn't need to go from 0 to 255. It can go from 0 to 1, or -3 to 3, or an arbitrary range with 0 value, with 0 mean. So it is just a matter of convention of what are the values that we keep in the images. But what is important is that gray images every pixel is represented by a single value, so that an image is at the end a matrix of values. So here we have an example of what is the importance of the number of bits in the representation of an image. So here we have an example. We have a tool that allows us to decrease the pixel depth. So the pixel depth is how many bits you are using, how many different colors you are using to represent your image. So if you use 8 bits, then you can represent up to 256 different values. If you use 7 bits, then you can only represent a half of those, so 128. If you use 6 bits, you can represent a half of those, so 64, and you keep decreasing the number of bits, then the number of colors that you can represent are fewer and fewer. So here we have the image with 256 colors, and here we have the image with 128 colors. So the maximum is still 255 or 254, but you go in steps of 2. So you go, instead of 0, 1, 2, 3, you go 0, 2, 4, 6, 8, etc. So now you have less number of colors, half of them, but still we don't see much of a difference between those. Now we go in groups in steps of 4, and still we don't see much of a difference. Steps of 8, 16, and still we don't see much of a difference between the two images. 3, and now we start to see some differences here in the background. Maybe they were visible before too, yeah, somehow, but not so much. When you go to only 4 colors in the along the range, now you see really the differences. And now this is a binary image where you have only 2 colors, 0 or 255. And the take-home message is that well, by controlling the number of bits, you can control what is the representation depth, so how accurate your intensity representation is. When we collect images in the camera, in the electron counting camera, each pixel is counting how many electrons have arrived during a particular period of time. So these frames that the camera is collecting, and this number of electrons go from 0, 1, 2, 3, and it depends on the time and the dose, but it rarely goes above 16, let's say, for a pixel. So that means that you need only 4 bits to represent those colors. So your colors go from 0 to 15, and if you take 2 frames of that sort, of that type, so each one of them have numbers between 0 and 15, and you add them, then you need a 5th bit for storing that result. So something else is averaging. So averaging is simply dividing by the number of frames you have summed. So summing and averaging is almost the same operation except for the division. So if you take 2 frames of 4 bits, you need 5 bits. If you add an extra frame with 4 bits, then you need a 6th bit, and so on. So it depends. It is not directly the number of frames that you have added. So that there is some. So if every frame goes from 0 to 15, and you are adding 10 frames, then your maximum sum goes from 0 to 150. And to store that number, you need 8 bits. Okay, so this is about how to encode an image. So let us continue with the presentation. So now what about the space? So let's say that we have a continuous pattern in space. So we have constructed a physical object that has this shape. So it has bands. These bands, let's say that the white part is a metal band, while the black part is an empty band. So we have constructed physically this object, and we illuminate this object and record the image. And there are also different configurations. So this is an angular pattern. These are vertical and horizontal patterns, each one of different width. What we see is that when we travel around this circle, for instance, we go from black to white and then black and white. There will be a number of pixels that are white, and then the same number of pixels approximately that are black, and then same number of pixels that are white. So this is a kind of wave. So this wave goes up and down like typical waves do. But what we see, and the same happens for every circle, what happens is that if you look as you get closer to the center of the pattern, you no longer see the ups and downs. So they are there because physically they have been constructed in a way that they are really there, but you cannot see them anymore. So what you see is a kind of blurry area where you see, instead of black and white alternating, what you see is everything gray. And the reason for that is that there is some part of the optical device that is either the acquisition or even your eye or the projector that is it is no longer capable of following these up and downs so quickly in space, and then this smoothing of going up and down, I cannot follow you, will cause to stay somewhere in the middle, and that is why we see it gray. And our eyes are very bad, or are low pass filters, and that is why when you look at the distance, you cannot see the very fine details. You have to get closer to see the fine details, because your eye doesn't have infinite spatial resolution, and then it cannot follow the going up and down of the objects, even if they are there. So for instance, that is what happens if you try to read a book from 50 meters away. You can the pattern going black and white is there, but you cannot follow it. Okay, so if you look at the vertical patterns, for instance, you can see that they really look like a sinusoid. So they go up, then they go down, they go up, they go down, and the transition can be rather smooth, like in this pink pattern. And as we said before, we cannot record absolutely every possible value in the space in the computer. So we need to sample our input structure, and we will do so by placing a sample on the up and down signal every fixed amount of space, every fixed length. So let's say that here it is represented with time, because time and space, they are pretty much similar in this regard. So we have the up and down pattern, and we put a sample at this distance, and then another sample at the same distance, and then another sample, and it doesn't really look like the sinusoid that is underneath, but there is a theorem that tells you that if you have at least 2 samples per period, then you can exactly recover the underlying signal. This is the Nyquist theorem. So here you have the example. So here you have a sinusoid, a period of that sinusoid, and then we have 2 samples in that period. We have these 2, and then we have another period, and then we have again 2 samples, and then we have another period, and we have these 2 samples, and so on. So as long as you take 2 samples per period, it doesn't matter if in the computer it doesn't really look like the perfect sinusoid, but you are able to recognize that you have that sinusoid, and you may relax that condition, or not that condition. You may not fulfill that condition, so you don't have any more 2 samples per period. So here, for instance, we have a period in which we have two samples, but then in the next period we only have 1. So we have, in this period we only have this sample. So that means that we are not fulfilling Nyquist criterion, and then we will never be able to identify that the underlying wave has this period. So that is, for instance, here it is very obvious. So from the samples alone, we would think that what we have is a much smoother wave. And let me see if these demos work, because some of them they were working with Java, and now browsers they don't like Java. But let us see if we can take a tour in this one. Okay, so let me see what is the so we cannot run it this one because we don't allow Java anymore in browsers. Okay, so why this is important? Because the wave in cryo-EM is the size of the object that you want to see, the finest size of the object. So we would all like to see things at a resolution of 1.2 angstroms, so that for instance, for an aromatic ring like this one, we see the hole in the aromatic ring, we see the individual atoms. But if you're not able to see these details, so then the smoother you go, for instance from 1.2 to 2 angstroms to 3 angstroms, the less details that you have in your structure. And this is the equivalent of going into very fine details. Very fine details would be at the origin, while the smoother details are at the farther away from the origin. So in this example here, all the fine details, they have been all blurred by the optical device, or by your inability to align correctly images, or by whatever reason. But if you want to see this thing at this resolution, and you want to see it in the computer, you have to guarantee that you are sampling at a pixel size that allows you to recover the underlying signal, because this sampling problem that we had here, because otherwise you might have the correct 1 angstrom resolution in your collected images in the analog signal, but if you don't sample it properly, then you will never be able to recover it from the computer image. So Nyquist would say that if you want to see something at a given resolution, so let's say 4 angstroms, then your pixel size has to be at least, or at most, let's say, 4 angstroms divided by 2. So that means you need 2 samples per wave. And typical sampling rate should be smaller. Instead of dividing by 2, it is suggested to divide by 3, because you need extra space in the Fourier space, and we will see later how this sampling translates into Fourier space. But you need extra space to commit or to accommodate interpolation errors, and you need a little bit more. Accuracy than the one given just by the Nyquist sampling theorem. Okay, so now we have an image inside the computer. So what kind of operations can we do now with it? So we know that this image is a matrix. So let's see what operations we can do with those matrices. So the first operation we could do is just at the matrix level. So we could take the matrix representing image 1. This image 1 is called Lina. This girl is called Lina. And we take the image associated to image 2, that is Barbara, and then we put some weights on those. So for instance, let's say that we multiply the first image by 0.5, the second image by 0.5, and we add the two matrices. So we have a new image, and this image will have half of Lina, half of Barbara. And we could give different weights, like putting more weight to Barbara, 0.75, and then 0.25 to Lina, or the opposite. And we would have more or less Lina or Barbara depending on our weights. So this is fun, but is it useful? Turns out that the images we collect from the electron microscope, they are very noisy. There are many different sources of noise, and one of the most important is the ice layer on which the electrons are, the samples are embedded. So basically what we are seeing here is the structure of the ice on top, and we have in the middle the structure of our particle that we are interested in. But we have in electron microscopy we have a signal to noise ratio that goes somewhere between 10 and 100 at the level of micrographs, and it is even much smaller at the level of frames. So this means that we have between 10 or 100 more times more noise than signal. Okay, but let's say that we have identical looking particles. So we are looking at our molecule. All molecules are exactly the same, and we are looking from exactly the same direction. So we can average all those images, and because the noise has zero mean, then the noise will tend to cancel out, and what we will see is the underlying signal. And actually, if you look at this averaging process, it has exactly the same structure as the one that we have presented for Lina or Barbara. So we are adding a collection of images, each one with a different weight, and the weight in this case is 1 over 1000 because we are averaging 1000 images. And then when you compute the average, this is what you get. So now you realize that what you have underneath is Lina, or that what you have underneath is this molecule. So averaging is really the way of getting rid of the noise that we have in the electron microscope. And actually, in a very simplistic way, all we do in electron microscopy is averaging in clever ways and looking trying to align the images so that they can be correctly aligned, but so that they can be correctly averaged. But all the whole problem is at the end averaging. So the 3D reconstruction is an averaging problem in 3D with many complications, but at the end it's averaging. And these operations that we can do at the level of images is also, or at the level of matrices, is also what is behind the 2D classification. So let's say that we have molecules that look like this, and we see kind of ball in the middle. So this is a virus, an icosahedral virus, but we cannot see the details for any one of these individual images. But if you identify which images look alike, and then you align them correctly, and then you take the average, then you get these very nice summaries where you have the you have removed much of the noise, and then you can see the capsomers of the virus very nicely with some fine details, and so on. So this is exactly the same operation that we were doing here with Lina, but now with viruses. And then we can, so we have performed operations at the level of matrix. Now we can perform an operation at the level of pixels. So it would go just to the other opposite side of the kinds of operations we can do. So let's say that when you have an image, this is a matrix of numbers, you count how often you see each one of the numbers. So let's say that we have seen number 30 this many times, and then number 20 this many times. We never saw 0, we never saw 255, and this tally of pixel counts is called a histogram. So the histogram of an image is actually it is an approximation of what is the probability that if I take a pixel at random, I get a particular value. So if I take a pixel at random within this image, the probability that I observe a value of 50, it is this count divided by the total number of pixels that I have seen. Okay, so the histogram is an approximation to the probability density function of the random variable that is taking a pixel at random and observing its value. And this can be very useful to perform some operations. So for instance, here we have a histogram equalization operation. It is also called histogram normalization, histogram operations in general. So let's say that we collect this image, and in this image we cannot see some of the details, and what we do is we compute the histogram of that image, and then we compute the cumulative histogram. The cumulative histogram is so the histogram is how often you have seen a particular value. So the cumulative histogram is how often you have seen a value that is this one or smaller than that one. So if we have 10 to the 5 pixels, then our maximum cumulative histogram, the maximum number, is the total number of pixels we have seen. So all of them, they have to be smaller or equal to 55. So now you can use this histogram, or this cumulative histogram, as a transformation of the colors of each one of the pixels. And to do so, what you will do is to rescale this maximum value to 255. So now your graph would go from 0 to 255 in X to 0 to 255 in Y, and then every input pixel, let's say that this pixel here has a value 200. So it has a value 200. I come to my curve, and then I see 200 should be substituted by this value, whatever that is, and then you substitute the 200 by this value, and you do the same for all pixels, and this is the result. And the result has a lot more contrast than the original image, and this is very much seen here in the cloud. So there was a cloud in the sky, but because it has so low contrast, so little difference between the pixel values in the cloud and the pixel values in the sky, we couldn't see the cloud clearly. But now there is much more difference between those values, and then we see the cloud nicely contrasted against the background. Okay, so let's see why that happened. So this image had a lot of bright values, in particular in the region somewhere around 220. It had a lot of counts. So this was, let's say, 220, this was 218. And then there was this little difference of 2 didn't allow us to see very clearly the cloud. But now, because the cumulative histogram has a lot of slope in this point, 218 will be mapped to, let's say, 218, but now 220 will be mapped to 230. So now the difference between these two neighboring pixels, it is amplified. So now the distance between the outcome pixels is much bigger, and then the outcome image, the output image has more contrast. So let's see this effect. Here we can see, for instance, what are the different operations we can do with the histogram or these pixel-wise transformations. So let's say that we have this image in gray scale, and then we transform. You transform the value. So the originally, let's go to the original. So originally is like this. So here we have the original histogram, and our transformation is almost identity. So if I take an input value of 200s here, so it will be substituted by 200s. But then I increase the contrast. So I increase the contrast in this area. So now all the values here in this area around the threshold where the high slope is, they become more and more separated. This is what I was mentioning before. The distance that originally was 2 or even 1 in pixel values, now they become more separated, and they can be separated by 2, 3, 4 or more the intensity values. But that comes for sure at cost. So the number of output values has to be kept the same. So the outcome will still be 0 to the output has to be still between 0 and 255. So you have to saturate somewhere. You have to sacrifice some gray value somewhere. A good area or good candidates to sacrifice are those ones that are not so much populated. So for instance here, there are no values between 0 and 50, let's say. So those are values that were not used by the original image. So now the output image can use those intensity values that were somehow spoiled, they were unused. And here it is the same. So here we didn't have those empty areas, maybe here a bit at the beginning. So that area can be sacrificed, but otherwise the remaining, they have to be collapsed into a single value. So typically you saturate at 255 and 0, and that is why this image looks almost like binary. So only very few gray values in between, they get a value that is different from 0 or different from 255. And of course you can go in the other direction, so you can make it more smooth, so that everything is almost mapped onto the same gray output gray value. So that is why now we have so little contrast in our images. Okay, so this histogram equalization is something that we normally do always that we show a micrograph and an image. So all images, no matter what the input gray values, they are always mapped between 0 and 255. So you compute the minimum, you compute the maximum of the input image, and then the minimum is mapped to 0, the maximum is mapped to 255. And here we have a histogram of the input gray values. And for instance, the viewer of Scipion and XMIP, they are tied to, they are implemented using ImageJ, and then in ImageJ you can have this tool where you can manipulate very easily the minimum, maximum. You can change the brightness and contrast. So these are a bit like the operations that we did with in the web. So you are transforming this curve that transforms input values into output values. And unless you do this, it is very difficult sometimes to see your particles in the micrographs. And you can do also this image normalization. You can do it at the level of micrograph, you can do it at the level of individual particles, and at the level of individual particles, the minimum and maximum, they are also marked between 0 and 255, and the minimum of each image is different between different particles, so the transformation between for all particles is slightly different between each other. And you can force, for instance, in the viewer to make all of them more consistent. So just a single transformation for all of them. So you compute the minimum of all, the maximum of all the images, and then you use that transformation. And you can really see the difference. So here, particles look like having different gray values. So this one looked to be darker than this one that was a bit brighter. And the reason for that is that might be this image had the brightest pixel, so that the maximum that is mapped to 255 makes the remaining of the histogram to be mapped to a slightly lower values. If you make a global transformation, a global normalization, then they all become more alike in gray values. And this is just something to keep in mind when you're looking at images, and this will also play an important role when you are doing 3D reconstruction. So when you we have seen already that these numbers in the matrices, you can manipulate them in any way that you like, and each manipulation is aimed to highlight different parts of the signal. But when you come to 3D reconstruction, you have to make sure that all the numbers that you're putting into the 3D reconstruction process that we already mentioned, it is kind of averaging. So you have to make sure that all the numbers that you are averaging are in a common numerical framework. So they cannot be numbers that are between 0 and 1, numbers that are between 0 and 2, and then you compute the average between those, because they are supposed to be representing the same kind of molecules. And then the numbers, they have to be consistent. And the way that it is typically done is by taking an area that in principle should have similar properties, and these areas in cryo-EM are the background of outside your particle. So you have your virus here, you put a circle, so there shouldn't be anything outside the circle, and then you make that outside, that is the image of the eyes, to have similar properties, in particular to have zero mean and standard deviation 1. This is the most common way to normalize now images. And in this paper here you have an analysis of all the different possibilities that at that time they were active possibilities, so they were not just theoretical ones, but there was a debate of what was the best way to normalize images. Now it is not any longer the case, so we are all normalizing in this way. Okay, so we have performed operations at the level of the whole matrix, operations at the level of a single pixel, and then we can do something in between. So for instance, we can make operations at the level of groups of pixels. So let's say that I want to transform this pixel in the middle with value 103, and my operation will do the following. So I will take the neighbors of that pixel, and then I will multiply each one of them by these numbers. So all the surroundings by -1, and then the central pixel by 9. And here you have the multiplication of all those. So 106 times -1 minus 106, and the same for the surroundings, and 103 times 9, it is 927. And then you add all these numbers, and the addition of all those numbers is 130. So you have you substitute 103 by 130, and then you move to the next pixel and you repeat the same operation. So this operation is called a convolution. Here we have a demo where we can perform the convolution step by step. So let's say that we are convolving the image that has these values, so 86, 40, 14, 82, and so on. We are convolving with this kernel. So when you do that, then for instance, you multiply. Let's start with this pixel here. So you multiply by 1 to 1, so that is 160, and then 58, and then this you multiply by 0 this row, and this one this row by -1, -2, -1, and then you add all the values. So the addition of all those values is 181, and then you substitute the central pixel by 181, and then you move to the next pixel and you repeat the same operation. So you multiply and then you sum. This addition of all this is 168, and then you substitute this central pixel by 168 and you move to the next one. And there is a problem with the borders, because in the borders, for instance here, if you move to the 1 pixel on the right, so let's finish this one. So if you move to 1 pixel on the right, then part of the kernel, this red numbers by which you are multiplying is called the kernel. Then the part of the kernel is outside. So what you do with the pixels that are outside? So you can multiply by 0, you can multiply by wrapping the image. So so you have come out on the right, so I take the leftmost pixel and I use it as if it was on the right. So this is equivalent to taking the underlined black image and repeating it infinitely on the right, on the left, on the up, bottom, and on the top, on the bottom, and so on. And actually that repetition is what the Fourier transform is doing. So the Fourier transform assumes that the input black image is repeated periodically along over space. Okay, so this is convolution. Let's go back to the what kind of operations we can do. And convolution is important because it models very well what is happening with the acquired images. So let's say that you have an ideal image, but the microscope is not able to visualize or to record the perfect underlying image, but it convolves it with a kernel. So the kernel doesn't look like this one with a kind of triangle, but the triangle illustrates very well what is the effect of the convolution. So the effect of convolving something with a kind of branch like this one is moving this image along this direction, and then what you are adding are multiple copies of the input image along this direction. That is why it blurs into that direction. And the same happens in this downwards direction, to the right, down, to the left. So we have multiple copies in each one of them. So the true shape of the point spread function, so this kernel is called the point spread function in optics, and so the true shape for the electron microscope is something round. So it looks like a kind of Gaussian, if you want. It is not a Gaussian, but if you want to think of it as a Gaussian, so it looks as a Gaussian, and then you are moving the ideal image in all directions. And by so one nice thing of convolution is that it is not always a bad thing. So if you design your kernel, we have seen the microscope is convolving, so that is bad because we would like to have access to the perfect image. But if you are able to design your kernel in a proper way, the information, the high resolution information that you have lost, you are able to recover it. And that is actually what it is done when you perform a CTF correction. So the CTF correction is designing the kernel with the right numbers so that part of the information that was lost because of the convolution of the microscope is restored. And also we can do it to do many other operations like sharpening. So the sharpening that you normally see in all astronomical images, or even in structural biology in cryo-EM, at the end of the process we do some sharpening. Many of those can be modeled as a convolution with the right kernel. So here we have some example of what are the properties that we can have with these convolutions. So for instance here this is a convolution that makes a blurring, so this would be kind of the convolution that the microscope would be doing, and the larger the kernel, the more blurred the image becomes. So you can see that for instance here we have very little blurring, just a bit, so we don't see the very fine details here, and then we have a little bit more blurring and even much longer blurring. So a large blurring kernel means that many pixels that are far away from the central pixel, they contribute to the final value of the central pixel. That is actually what happens when you use the microscope with very large defocus. So the associated kernel to very large defocus is very large. So that means that information that was very far away from the central pixel gets mixed into the central pixel. And when you decrease the defocus, then you are decreasing the point spread function. So now the information content is much more concentrated, so that the values from a pixel, they only become from a narrower area around that pixel. But blurring is not the only kind of operation that we can perform. So we can use, for instance, kernels to invert images. So for instance here the central value is removed, and that is also something that the microscope is doing. So it is removing the constant, the DC component of the image, or the very low frequency component of the image, so that we haven't seen those things like the concept of low frequency and so on, but the middle. So let's say that these values are around 128. After convolving, they are no longer around 128, but they go very close to 0, so they may be around 10. And then we can have kernels that can compute borders. So for instance here this one is computing vertical borders, or this one is computing horizontal borders. So that is why, for instance, this fiber here, it is seen in this when you apply this kernel, but it shouldn't be so visible when you apply a kernel that computes vertical borders, because it doesn't have a vertical border, it has an horizontal border. So it has a border only when you travel in this direction, not when you travel in this direction. So these edge detections, they are also part of some of the operations that we do in cryo-EM. And here, for instance, the sharpening that we do at the end, just to highlight the high frequency components, and that there are many subtleties about what is the right amount of sharpening and why you should do sharpening, and well, there are many issues there. But all this sharpening, not all, but many of these sharpening operators, they can be thought of kernels that are convolving your image with the right weights in each one of the pixels. Then another application of these group level operations is that smoothing is not always wrong. So for instance, it depends for what. So you might have the raw micrograph as we have it here on the left, but there is so much noise that we cannot see properly the particles inside. So you can convolve your micrographs with some blurring kernel, and the blurring kernel will remove a lot of that noise, and then it will allow you to see better your particles. So depending for what, for instance for particle picking, blurring can be good. Another nice application of the convolution is that if you convolve with an object that you are looking for, then the output of the convolution will tell you where the maximum, what that object is. So for instance here what we have is, let's say that you want to pick the eye of this bird, so you assign a kernel that is actually the eye of a bird, and then you convolve it on the whole image, and because of this convolution you will have one of the output values will be the maximum, and this maximum is exactly at the location of the eye of the bird. And this is actually part, not the whole story, but it is part of the story that is behind picking. So one of the steps is convolving with something that looks like your particle. And so for instance here we are trying to detect this kind of viruses, and then part of the story is convolving the input micrograph with the kernel that looks like a virus in a way that we can identify the local maxima, and then decide whether those local maxima really correspond to particles or not. So here probably we have also some other local maxima, but they have not been the algorithm that decides whether that local maximum is really a particle or not has decided that it is not. And this is important because what we will see later is that very often some particles are missed, and many other that are really non-particles, they are accepted as particles in the micrographs, and then so these decision algorithms that come afterwards, they really become very important. Some other operation that we can do with images is some geometrical transformation. So we may have this input image, and then we may want to rotate it, or we may have this input image and we want to make it smaller. And in this kind of geometrical transformations, what we need is a function that tells us every coordinate at the output image where it is coming from which coordinate in the input image it is coming from. So this one is coming from here, this one is coming from here, and so on. So then you take every pixel in the output image, and then you try to copy from the input image, but then because of the sampling, it turns out that you don't have those values anymore. So they were present in the analog image, but not in the digital image. So I want to copy for this pixel, I want to copy this pixel here, but I don't have it. So all I have are these 4 other values in the surroundings. So I will have to interpolate the value at the middle, and that interpolation can be done in many different ways. So here is a possibility. So let's say that I have 4 values in the corners, so those are the measured values, this 116, 191, 239, so on, and I want to interpolate the value here in the middle. So what I can do is take those 4 values, fit a plane, and then evaluate the plane at the location I'm interested in. and then the evaluation of that plane here would be 172. That is a value that is somehow in the middle of the 4, and it gives more importance to the pixels that are closer. So if I have to evaluate the plane at the location that is very close to this 191, it will be close to 191. And one of the things is that there is a unique plane that goes through all those 4 values, and this why restricting to just 4 values around? I could take the 16 values around, and then I would have a better estimate of what the central pixel is, and the central the 4 pixels around, it is just gives you an idea of what are you can construct just a continuous function that is compatible with those observations. But if you take more information around, you are able to construct a function that is not only continuous and compatible with the observed values, but it is also whose derivatives of this continuous function are also compatible with the derivatives you have observed. And you can also, again, you cannot be restricted to 16. You can go as far as you like, and the farther you go, the more complex your function, the continuous function, will be. And for instance, if you take 16 values around, it is called the bicubic interpolation, bicubic, because in each direction you have a cubic polynomial. Here it is called the bilinear interpolation, because this plane in each direction, what you have is a line. And okay, good. So this I had a demo here, but it doesn't work any longer, so I cannot show you. But if you use a bicubic interpolation, for instance, the quality of the interpolated data is much better than if you use just bilinear interpolation. And especially when you accumulate interpolation after interpolation, that is an operation that all software packages try to avoid, then these interpolation errors may accumulate, and then what you have is a quite degraded image at the end. And we saw that making the image smaller, you can do it also through this geometrical transformation framework in which you have to interpolate, but you can also do it through an operation that is called downsampling. So the downsampling is, for instance, or binning. Binning is just a way of doing downsizing of the input image. Downsampling is the other way. So the binning is very simple. So let's say that I want to make the image twice smaller in each direction. So you take big squares of size 2 times 2 and compute the average of the 4 values that you have in the original image, and now you have a single values, and you do the same for the next square and for the next square. So at the end, this is like having a sample here, here, there. So the new sampling rate is k times, in this example it is k equal 2, or k equal 4 if you make bigger squares. So it is k times the original pixel size. And remind always of this Nyquist constraint. And the problem with this binning operation, it is that it is the worst way of making small images. So this in a way can be thought of convolving the original image with a kernel that has ones in all these pixels, and then taking a sample from the convolved image. And you can design much better kernels. And here you have a paper in which we discuss different kernel constructions. And the one of binning is really the worst. And the best one is the Fourier cropping, but we haven't seen Fourier yet. So here it is where we see Fourier. So Fourier is another family of operations that we can do on our images. So what we have seen so far are images at the level of matrix, of the full matrix, operations at the level of a single pixel, and we have also seen operations at the level of groups of pixels, and the Fourier transform is again operating on the whole image. So it is transforming the way we interpret images. So the way we interpret images, you can think of these images as having so you can decompose this image as an image with just one pixel, that is this leftmost top left pixel, and then the second pixel, another image with just one pixel, and another image with just one pixel. So all these images with just one pixel, they're called delta functions. So instead of being the addition of many delta functions, you can think of an image as being the sum of waves. And this is very nicely illustrated in one dimension. So let's say that this is our input image that we have plotted in one dimension. So our black and white pixels, if you want. So all these pixels would be white, all these pixels would be black, and then white again, and then black again. And we can understand this set of pixels as a sum of waves. So we would have first a wave that follows more or less the general trend. So this going up and then down and then up. So this is exactly following the same periodicity. And then on top of that wave, we have to add some other wave. And this second wave, it turns out that if your signal is periodic, then the second wave is the period of the second wave is 1/2 of the period of the first wave. So the first wave defines the fundamental period, and the second wave defines an harmonic of the fundamental period. And then you have the third harmonic, whose period is 1/3 of the original, and then the fourth harmonic, that is 1/4 of the original period. And by adding all those waves, all of them with the right period, the right amplitude, and the right phase, and the phase is just moving these waves to the left or to the right, then we will be able to approximate the input image to an arbitrarily good accuracy as we like, except again there are always many details, and for instance discontinuities cannot be well approximated and so on. But as long as you have an original digital image, you can have, by adding these waves, you can have an exact approximation or an exact reconstruction of the input image. And here it is a picture of how waves in 2 dimensions look like, because we have seen waves in 1 dimension, but the waves in 2 dimensions, they look like this. And then so they go up and down, like the standard waves. They have amplitudes, that is how intense or how much contrast you have between the higher peak and the lower peaks. And you have also, because now you are in 2 dimensions, you have an orientation. So this wave is propagating in this direction, and you can change the orientation, and you can also change the phase shift. So the phase shift in 1D was moving the wave to the left or to the right. Here we are moving the wave to the left or to the right, but along the direction of the propagation of the wave. So this wave is propagating in this direction, so it moves to the left or to the right in that direction. So you can see, for instance, here it has 0 phase, so that means that we have a maximum at the origin, but now at the origin we no longer have a maximum, but the maximum is a little bit shifted. And let us see some other ideas regarding these waves. So these waves, and again we cannot run it because of Java, but these waves have frequency. So we have been talking about the period. The frequency is the inverse of the period. And what we have here is that we can have waves that are slower. So those are called low frequency waves, and that would give you the overall shape of an object. And then we have much faster waves like these ones here with a much smaller period, so that means high frequency. Actually, the wave that has the lowest frequency is 0, so that is a constant, so there is no, the period is infinity, so that is there is no variation over space, and that is a constant. That is the definition of a constant. Okay, so let's use our waves to reconstruct images. So now, if I have an input image like this one, what I can do is to annotate what is the amplitude and the phase of each one of the possible waves. So we have different orientations, different periods, so I can annotate for each orientation and each period how much amplitude I need from that wave. And this is what I'm representing here. So we are not talking for the moment about the phase shift, but just the amplitudes. And the amplitudes are also called intensities, and they are related to energy, so how much energy you need from that wave. And here is some examples. So let's say that we have, for instance, like in this house, we have the wall of the house. So the wall of the house, we need a vertical wave of a given frequency of a given period. So we annotate that, let's say that this is the correct period. So somehow this is frequency axis, so this is the inverse of the period. So this frequency is associated to this period, and then we annotate that we need a lot of energy from that period. And because this is a technical detail, but you can have orientations that go from all over from 0 to 360 degrees. So you have to annotate that you need this period and also this period, the one that is traveling in the opposite direction but is also vertical. And here is the 0 frequency. So the 0 frequency is just a constant that allows us to plot this image. And then we have other waves here, like for instance the door. So the door is the highest frequency that we can have in this figure. So it is 1 pixel white, 1 pixel black, 1 pixel white. That is the fastest you can go in a digital image. And we need some energy from that wave. So we annotate that we need energy here and there. And then we have other interesting waves like this one. This one here is the roof of the house, and then what we realize is that this wave is not symmetrical. So the wall is symmetrical, so the length of the white bars is the same as the length of the black bars, and then we have here white areas that are wider than the black parts, and this is so we need a wave. So this is this wave that propagates in this direction. So it is, but the fact that they are not symmetrical makes you require harmonics. So I need the second harmonic, the third harmonic, and the fourth harmonic, and so on. So non-symmetrical structures require harmonic from the fundamental period. And you could go on analyzing the windows. So these windows here, so this window is this one, this window is this one, and you may identify all the different parts of this house. But natural images and macromolecules are kind of natural images. They don't have these waves so nicely seen. So that means that you will need a continuous from all possible frequencies. So you will need a little bit of energy of all frequencies to make up the image of Lina or the image of this monkey. And we have not been talking about the phases, but the phases are also there, so you could make similar plot with now the phases. And here is a plot in which we are encoding energy and phase in the same figure. So we take the input image of a DAC, and then we compute the Fourier transform, that is how much energy and phase you need from each one of the waves. And here we are plotting, if we have a strong color, that means that we need a lot of energy, and the color itself is the phase. So we do the Fourier transform of a DAC, the Fourier transform of a cat, and here is the corresponding Fourier transform. And now these are now we take the amplitudes from the DAC, and we take the phases from the cat, and we do the inverse Fourier transform. And by doing the inverse Fourier transform, what we have is mostly the cat, but with some errors. So that means that most of the information of how the image looks like in the Fourier space, they are kept in the phases rather than in the amplitudes, and this has a lot of consequences. And in cryo-EM we are recording amplitudes and phases at the same time, while for instance in crystallography they can only record the amplitudes, and then the phases have to be inferred computationally. So that is one of the main advantages of cryo-EM. The disadvantage is that this amplitude and phases information is embedded in a lot of noise. So we saw that before that our signal to noise ratio was somewhere between 10 and 100, so 1/10 and 100th. So that means that we have 10 or 100 more times noise than signal. Okay, but once we understand that, we may try to define operations in the Fourier space that are helpful. So for instance, here we have a couple of examples. So in the first column, what we have is we have an image, we have the Fourier transform. Here we are representing again just the amplitudes. We see that we require a lot of energy from very low frequency components, and then there are some components along this direction, and the remaining directions they don't have almost any energy. And we understand now why this direction, because it is the direction of the waves. So we can see here kind of wave propagating in this direction, so that is why we need all these energies here. But then we define a kernel now in the Fourier space such that the central area is multiplied by 0. The coefficients inside this donut, they are multiplied by a number different from 0, and then outside the donut they're again multiplied by 0. These kind of filters, they are called bandpass filters, and they are very much used in the image processing. You have low pass filters. So in the low pass filters the kernel looks like a circle, so no hole in the middle. You have high pass filters, so it is just the opposite, so you keep the high frequency and you remove the low frequencies. And for this bandpass, for instance, in this particular bandpass filter, so after multiplying we have removed all the energy at the very low frequencies, so that is why you don't have it here. But you keep this energy in the donut, and then when you do the inverse Fourier transform, this is what you get. And so you have isolated from the original image the components that are in this area of frequency, and these are these fine details. And if you compute the difference with the original image, then what you see is mostly the low frequency components that were killed by the filter. and you may define your filter based on the location of the energy, but you can also define your filter as a function of the amplitude of that amount of energy. So you, for instance, let's say that you have this image that is a noisy version of some acquisition, and then you do the Fourier transform, you measure the energy at all possible frequencies, and then you remove all the coefficients whose energy is smaller than a threshold. And then you do the inverse Fourier transform and you compute the difference. And the difference is just the noise. So what you have here is a much cleaner version of the original image, because the energy of depends on many things, but the energy of noise tends to be more or less equally distributed, while the energy of your signal tends to be concentrated at a few normally low frequency components. So by identifying those components that are more likely to come from the signal than from the noise, you're removing a lot of noise. Here you have this idea. So let's say that you have a perfect image. This is a simulated example. So we have a perfect image, we have noise, we add, if we analyze the Fourier transform of those, and I'm taking just a profile through those power spectra, we would see that the power spectrum of the signal is very much concentrated around the zero frequency, so around the low frequency components, while the Fourier transform, the amplitude that we require for reproducing noise, it is more or less spread all over the place. When we superpose both, the noisy image, so the image plus noise, has this shape. So that means that for some frequency components we have more signal than noise, but for some other frequency components we have more noise than signal. And actually that is why we require many particles to have high resolution 3D reconstructions, because the more you average, the red component that is coming from the signal stays the same, but the components, the blue components that are coming from the noise, they get lower and lower and lower at all frequencies. This is the same effect, but now in frequency domain, than the one we saw with Lina and averaging 1000 images of Lina. Okay, so here we have the same idea, but now what we are plotting is in which area you have more signal than noise, but now looking at the full power spectrum rather than just one line of it. So this would be the power spectrum of the original image, the power spectrum of the noisy image, and then for these blue points we have more noise than signal, and for these red points we have more signal than noise. The problem with real images is that you never know for which coefficient you have more signal or noise. So, but in principle this is happening also for real images, only that you don't know which coefficients to keep. Okay. And something also very nice of the Fourier transform is that you can define your filters in very specific ways. So for instance, let's say that we have the electron micrograph of a crystal. So a crystal is a repetitive lattice of macromolecules. And this repetitive lattice, you have a lot of noise on top, but because it is repetitive, it happens like with the house. So the Fourier transform of the house, you will require energy from a specific frequencies. So here it is displayed as we need energy from these black points. And now you can define your filter just to isolate the points, and this in crystallography they are called reflections. So just to isolate the reflections that you are interested in, and then you do the inverse Fourier transform, and now you have a much better, a much cleaner version of the image underneath, and what we have removed is just the noise. It is just the same as we did here in this example. So it is the same as we did here, but now by designing our kernel based on the location of the Fourier coefficients, and the maximum reflection that you keep is the maximum frequency that you have. The frequency is measured in angstroms to the -1, so 1 over angstrom, and the frequency is the inverse of the period, and the period is the resolution that we are interested. So when we were saying at the beginning, I'm interested in reconstructing my molecule at 1 angstrom resolution or 2 angstrom resolution, we are talking about the period. That the period is measured in angstrom, and the frequency is the inverse of that period. Okay, so here let's say another operation that we can perform in Fourier space is the deconvolution. So the microscope is convolving, but you can define operations in the Fourier domain that are aimed to restore the aberrations of the microscope. So let's say that we have this ideal image, but we cannot have access to the ideal image, but in a very simplified way, the image that we have is that one convolved with a PSF. And very simplified, because this PSF may not be the same all over the place, so you have to make careful corrections locally, and also because we are forgetting about the noise and even more subtle details, because the exact model of the microscope, it may not be a convolution, but some other non-linear operation. But let's keep it simple. So it happens that our observed image is the ideal image convolved with the point spread function of the microscope. If you do the Fourier transform of that equation, the Fourier transform has a property that a convolution in real space is a multiplication of the Fourier transform of each one of the components you are convolving. So it would be the Fourier transform of the ideal image multiplied by the Fourier transform of the point spread function. So in a very simplistic way, a very nice way of recovering or estimating the ideal image would be, okay, so I only have to divide by the Fourier transform of the PSF, that is the CTF. So this contrast transfer function is the Fourier transform of the point spread function, and then I have an estimate of how the Fourier transform of the ideal image looks like, and I only need to do the inverse Fourier transform to recover the ideal image. So it is not exactly the same as the original one, and the reason that it is not exactly the same, it is because we have not accounted for the noise, and maybe our model of what were the aberrations is not perfect. But otherwise, it is a much better estimation of what the ideal image looks like. There is another complication in electron microscopy, that is that the CTF, that is the Fourier transform of the PSF, crosses zero at given frequencies. So that means that the information at those frequencies have been completely lost, and this complete loss of information makes that you cannot divide, you have multiplied by zero, so you cannot divide by zero to recover the original information. There is another nice implication of the Fourier transform along the processing, that is the central slice theorem. So the central slice theorem relates the Fourier transform of an object to the Fourier transform of a projection of that object. So let's say that you have a macromolecule in 3D dimensions. Then you make a projection, that is what the microscope is supposed to be doing. And so what you have is the collapse of all the information along this path into a single pixel. So you had here three-dimensional information, now you have only two-dimensional information. And the center slice theorem says that if you take the Fourier transform of this projection, that is another 2D image, and you do the 3D Fourier transform, so there are also 3D waves, so you do the 3D Fourier transform of the original object, then these coefficients here are exactly the same coefficients that you have in a central slice of, so central means going through the origin, in a central slice of the 3D Fourier transform of the original object. So these coefficients are exactly these ones. Exactly, again, there are always a lot of details, but in a very good very good intuitive way, they're exactly the same. And then that allows you to perform 3D reconstructions, because when you have an experimental image like this one and you have a reference volume like this one, so you are trying to figure out, okay, so this experimental image, where am I looking from this 3D object? So this must be some projection along some unknown direction of this object. So all I have to do is to project this object in many different directions, and then compare this experimental image to each one of the different projections, and then decide that this one is most similar to this one. And for that we are using the correlation that we learned with the bird and the eye of the bird and so on. And then decide that this image, this experimental image, is most similar to this one. And since we know from where this image was taken from here, so we assume that this image is also taken from here. And you repeat the same for all the experimental images. And now you have the orientation of each one of the experimental images, and then you can do the 2D Fourier transform of all of those. And because you know that these 2D Fourier transform are exactly the same, that they have exactly the same values as the 3D Fourier transform, now you can place them back, these 2D Fourier transforms, you can place them back in the 3D Fourier space, and then do a 3D inverse transform to recover your macromolecule. So that inversion, as always, there are many details because we are forgetting about the noise. So the noise makes that the Fourier coefficients are not exactly the same, and they're not consistent with the remaining of the images and so on. But that idea of first I need to find the orientation of each one of the experimental images, and then I have to fill the 3D Fourier space with the 2D Fourier with the Fourier coefficients of the 2D Fourier transform of the input images, then that is really behind many of the current 3D reconstruction algorithms. And before finishing, I would like to introduce some operations that are also done on images that are very common now. So you may have heard about these deep learning algorithms. So deep learning algorithms, they are coming from computational domain that are called machine learning and neural networks. So the neural networks, they were originally designed to try to mimic the behavior of a biological neuron. So a biological neuron receives information through the dendrites, then it is processed in the nucleus, and somehow it is output through the axon to the next neuron. So a possible way of mimicking that is this one. So we have different information. So information from the input will be represented by these x0, x1, x2 variables, and then the nucleus combines that information and it gives different weights to each one of the inputs, and this is what the cell body would be computing. This is a very simplistic model of what the cell body would be computing. And then it may add its own bias, so it may add a constant to that input information, and then it outputs this addition through the axon. And then for this output, what we use is a non-linear function. So this computation that is performed at the cell body goes through a non-linear, it is called activation function. But then these biological models, they grew up in a complete domain of itself. So they have this origin, but now this kind of functions, they make sense by themselves in machine learning, computation, and actually they can be regarded as a regression model. So given some input information, so this input information, these blue points would be the coordinates. You have x, y, so the x and y would be the two inputs to the neural network, and then the neural network can be thought of computing a kind of regression to the observed values. And you can be very creative about the way you construct neural networks, because we have seen just one neuron. So each one of these circles would be a neuron, but then so you have the neurons at the input, but then these neurons at the input may be connected to some other neurons, and these neurons are connected to some other neurons, and these neurons to more neurons, and each one of the layers of the neuron is a layer. So this is the input layer, this is the output layer, but then you can have many layers in between, and these hidden layers are the ones that are why this domain is called deep, because you have many layers, and that is why they're called deep. And you can there have been several advances that have made this deep learning to rocket in the last years. The first one is that you need a lot of data to train the network, but for instance in cryo-EM we are lucky that we have a lot of data. And then also this requires a lot of computation, and that is why we need GPUs that are much faster to do this kind of computations. Graphical processor units, that is what GPU stands for. And then the final thing, and this is very important, is that you are able to estimate what are the weights between the connection of the different neurons. And these weights, they are parameters that you have to optimize and find for making this regression. So if you are familiar with regression, in a regression of a line, for instance, you have the parameters of the line. So you need to find those parameters, and that is where all this stochastic optimization have been really improved a lot, and they allowed for finding the parameters of your model in a safe way. So stochastic optimization is different from deterministic optimization in this way. So let's say that you start from here and you want to find the optimum of this function here. So there is a valley at this point. So the deterministic optimization, one of the most famous one, is this gradient descent. So a gradient descent goes in the direction where this slope is maximum. So you go through the direction of the maximum slope and then you find the minimum. But this is very good for local minima. But if you have a lot of local minima, like in these profiles, in these landscapes, then it might be better to make random movements, and in general they move in the right way, but so in the direction of the minimum, but very often they go in opposite ways, and these opposite ways allow you to escape from local minima. So it allow you to go from this local minimum to this other local minimum that is also the global minimum. And you can be very creative about the way that you can construct your network. So you can make the connections to so the neurons to be connected to each one in many different ways. We have just seen the multi-layer feed-forward network. And you have also different kind of neurons. So we have seen the simplest way a neuron can be constructed. So that would be one of these hidden cells, the ones without any drawing in between or any symbol inside the circle. But you can have, for instance, neurons with feedback, so the output of that neuron can be the input of itself, and you can be really creative. Here you have some examples, and then again you can construct many very complex architectures. This is one of the simplest ones, but just to give you an idea, so you have every one of these blocks is 64 layers of these neurons, and these 64 layers, they are connected to these 32 outputs. So you start with something here, then you convolve. Actually, we haven't been talking about that, but the weights can also be made to be convolutions. So that is a very effective way of reducing the number of weights that you have to compute. So, for instance, here you're convolving with 3 different kernels, and then these 3 different kernels you are convolving with 32, you are producing 32 layers, and then convolving with 64 kernels to produce 64 layers, and then you can make a max pooling, for instance. This max pooling is just a sampling, and we have seen all these operations, and what here it is just gives you an idea of how complicated these things can be, but at the end, if you are able to estimate all those weights, they can be very powerful in making regressions. And regression is just learning a function that you want, and in our domain, learning a function can be aligning 2 images. So given 2 images, tell me the angle between those 2 images, or can be given an image, tell me what is the denoised version of that image, or can be give me what is the enhanced, so this sharpening, and you can be really creative there. And somehow it is said that it has been shown that the first layers tend to learn low-level operations or low-level kernels, and then the higher you go into, or the deeper you go into the network, the kernels, they look more like high-level kernels, so high-level objects. So in conclusion, we have seen that the quality of an image depends on its bit depth and the sampling rate. So how fine you sample your image in space and in colors, and then you will have a matrix of numbers, and then with those matrices of numbers, you can do many different operations at the level of full image, of pixels, groups of pixels, geometrical transformations, transformations in general, like the Fourier transform. Fourier transform is one of the most important transformations that we can do, but those are not the only ones. So, for instance, we have the wavelet transform that somehow it has been used in the field. And in the recent years, this deep learning have has revolutionized the image processing domain, and it is getting more and more incorporated into cryo-EM. So that would be all, and I hope you find this video useful.